Thanks for joining me for example 4.1.3. In this example, we're going to see how the formula for the line of best fit, or the regression line, sometimes called the least squares formula, can be obtained using multivariable calculus. So the idea here is that we have n observation points, endpoints x1, y1, up through xn, yn, and the goal is going to be to find parameters m, which is the slope, and b, the y-intercept, so that the line y, which is f of x, is mx plus b, this line here, minimizes the sum of the squares of the vertical deviations, which are these distances here. So the vertical distances from the point, the sum of all of these distances to the line of best fit must be as small as possible. So the sum of the squares of the vertical deviations is, if we've got endpoints, we're summing from 1 to n. In the rest of the example, I'll leave these indices off for simplicity. But you're taking the function value minus the y value of the observation. So function value minus y value, function value minus y value. Now the function value is m of the x plugged in, so m of xi plus b minus yi. Now we're summing these up and we're squaring those deviations. Since the xi and yi are all observations, they're all constant. And so the only thing which are, well, unknown is the m and the b. So we can think of this as a function of two variables, e for error, of m and b, where it is exactly this sum of the squares. The sum of m times xi plus b minus yi all squared. We would like to find m and b so that this e, this error, is a minimum. So we're going to do exactly what we've done in the previous examples. We're going to find the partial derivatives of e, and we're going to set them equal to 0. So let's start with e sub m. Now, if we're taking the derivative of this expression, we're taking del by del m, and we can switch the sigma and the derivative, so we can take the derivative of the term that's inside. So we're going to have the sum, and we'll take the derivative here. Now m is the variable, so we have a square. That means we have a chain rule, so we have got to do 2 times, and we'll keep the same inside, m xi plus b minus yi. But now we also have the derivative of the inside, and if m is the variable here, then we have to multiply by xi. Now, we're going to need this expression, so let's clean this up a little bit. Let's expand through, so we'll get the sum of 2m xi squared plus 2b xi minus 2 xi yi. And then using the properties of sigma notation, we can distribute the sigma and bring out the constants. So the constants now are the m and the b and the 2, because the I is what's changing in the subscript of summation. So let's bring out 2m, and we'll have the sum of xi squared plus 2b, the sum of xi, minus 2, the sum of xi yi. Now, we want to let this equal to 0, so we'll let e sub m equal 0, which means that we can cancel out all the 2's, and we'll bring the negative over to the other side. So we will end up by having m times the sum of xi squared plus b times the sum of xi is equal to the sum of xi yi. Let's do the same thing for e sub b. So e sub b, here we're taking the derivative of this expression with respect to b, so I can interchange the sum and the derivative. We need a chain rule again. So 2mxi plus b minus yi, and then the derivative of the inside with respect to b, well, we're only going to get 1. These things go away, and the coefficient of b is 1, and so we're done. Let's clean this up again a little bit. So the same way we can distribute the 2 and pull out the constants, we're going to have 2m, the sum of xi, plus 2 be the sum of 1 minus 2 the sum of yi. And if we're adding up 1 n times, we're just going to get n for this term. So this is going to be 2m the sum of xi plus 2b times n minus 2 the sum of the yi's. Similarly, let us let e sub b equals 0. I'm going to do the same thing, cancel out the 2's and bring the negative over to the other side. So that will give me m times the sum of xi plus 2bn is equal to, no, the 2 has gone away, plus b times n is equal to the sum of the yi's. We have two equations which have to be true at the same time. So we have a system of equations here. Now the unknowns are m and b. So let me rewrite that. We have the coefficients, the sum of the xi squared times m, plus the sum of the xi times b is equal to the sum of xi yi. Next equation, we've got the sum of xi times m plus n times b is the sum of yi. Two equations, two unknowns. We want to solve for m and b. So we could do this in a host of different ways. I'm going to do Cramer's rule that you will remember from your linear algebra course. And Cramer's tells us, well, let's solve for m, that we're going to have a ratio of determinants. The denominator is going to be the coefficient matrix. So the sum of the xi squared, the sum of the xi, the sum of the xi, and n. And the numerator is going to be the coefficient matrix, but with the x column replaced with the constants. So the sum of xi yi times the sum of xi, the sum of yi times n, which gives us the determinants you'll remember as AD minus BC, or this little cross product, little motion, subtracting in between. So we're getting n, the sum of xi yi, minus n, the sum of xi, the sum of yi, divided by, on the bottom we have n, the sum of xi squared, minus the sum of xi times the sum of xi, so the sum of xi squared. And that is, in fact, the right formula for the slope of the line of best fit. Now, there's more left to do, right? We would have to do the same thing, so the same for b, and show, in fact, that this is a minimum. But this really does turn out to be, we're not going to do this. We'll just sort of leave that as an exercise, or for you to believe that this is true. But you should recognize, if you've seen the formula for the line of best fit, that we have obtained the correct slope for it here. And it should be said that multivariable calculus is not the only way of finding the equation for the line of best fit. Linear algebra also provides a technique for doing this. In the next video, we will look at absolute extrema and start section 4.2.